I'll just start the coding. Okay, so I hope you got my screen, right? Did anyone get my screen? Or with a then technical difficulty, you can see some white screen, right? Hello. Can you answer in the chat or just unmute and tell? Do you get the screen? Okay. So okay. So then we will start with the linear algebra with vector spaces, right? Okay. So vector spaces, let's say, because there are a few axioms, I think you can define it in like many of the ways. If you define a vector space, there are many definitions what vector space really is. Mainly, you can have up to 11 axioms, right? I think, yeah, it is 11. Most of the time, it is 11 axioms. Also, you can divide it to two groups. I think it is given in the note. So it is like the defining part. It is not much important how you define, but you need to know what are the properties of the vector space. So it is a it is the vector space. The first confusion you guys know, because sometimes if I say a vector, you guys imagine something like this, right? So it is say 2, 3, 4 or something like this. If you say something a vector, you would like imagine this as this some definition you guys heard from the A levels, some also from beforehand, before knowing take into the subject. You will learn this as something which has a magnitude and direction. So this is not false, but this is not actually correct, right, regarding the vector spaces. Because if you like see what is actually a vector space, in single we call it a so it is not something with a direction. It means physical direction, right? Because if it is, because if we deal with some vectors with something like this, right, we deal with previously, it is only a one kind of a vectors, right? We call it a real vectors or any other thing. You can have velocity and acceleration, any of these are vectors. These are like some physical vectors, and they represent some physical quantities. So you can always have some physical direction to that. But in actual case, vector is nothing to do with just geometrical case, right? It means when you call it a vector, it is not something with the actual direction. It has some direction, but it is not an actual direction. So I will define first a vector is some object. Better it define it as some mathematical object. Let's say some variable or something which has certain properties. So first thing you need to know to like understand this subject, to get rid of the the mentality that vector is something with the direction, like it is something like a velocity, acceleration. This is only a one part of the vector. So you have to break this limitation. So from this point onwards, you need to think vector as some object, right? Okay. So then if you're defining a vector, there are typical ways. Basically, you have several properties to define a vector space, right? So there are properties. Actually, it is better I can share the note with you. I think it is pretty much clear than this, right? So this is actually not what we get. It is some old note. So here, if you define a vector space, it is something, a concept, that vector space, you can think of it as a vector space is set of vectors. It means it is some sort of a group or set, or let's say it is a collection of vectors. If you take some collection of vectors, if it has these properties, we call it a vector space. It's just a definition. So first property is, actually you have two vectors. Actually, I think it is better to share the whiteboard. I think otherwise I will be just reading this, right? Let's say I just go through, I'm not going to this all the 10 of these, but just going to the the basic idea of what vector is, right? Okay, what happened? Okay, wait a minute, I think my screen share is not working. Okay. So uh, I hope you will get my okay. You are getting my screen, right? I think it is shared now. So let's say in vector space, there is something called a closure property. It means if you get some vector space is V, let's say V is a vector space. You take some two vectors, let's say A and B, or any other letter you can choose, right? This is inside this vector space. You can say the addition of these two vectors also inside this vector space. This is we call a closure property. It means if you take any of the two vectors and perform this addition operation, the result you get is also a vector in this vector space. Let's say something like this. Let's say it is something like this. If you have some two points in here, let's say this is A and this is B. This is some sort of set. And A plus B, it is somewhere here. It means your summation is outside your set. Then you cannot actually, it is actually not work, but by defining this operation on this set, with only having our vector space, it is like it is something like if you have something another set which falls into this addition, that's another story, right? But if you want to talk about vector addition and do your operation on this vector space itself, you need to have this closure property. It means your addition should lie on your space. Also, you have these properties. They are like commutative law and any other case. That's all other properties that you have learned in before the vector, that you have done the geometrical vectors to this let's say accelerations, velocities, and so on, are all other applications applied here. It means if you take the addition of two vectors, A plus B is no different from B plus A. So this is like commutative law. This is actually the same. If you get two there's are two 10 rows and I think one additional law, one additional rule. Those two criteria are nothing but everything we do with normal vectors, we just describe it as some sentence and we define it as a rule, right? It is nothing more than that. The thing you done with all the ordinary vectors you learned up to now is some sort of like this, right? You don't have to memorize these things. But if someone says, if you some set and operation to tell this is a vector space, you have to memorize these laws, right? I don't think there will be much problem. I think I will give you some problem. Let's say, okay, so I think, so then it is some sort of like thing, because if you have vectors, these 10 criterion are satisfied, what you have to do, if you give some set and to prove this as a vector space, you have to check each of these 10 rules to verify it is a vector space. But it is slightly different way to given it to you. So it is, I think there's some sort of difference of field and other things, and the definition of vector space a bit different. But I think the note I shared you, there are some 10 rules. So you can use that rules to prove the vector space, because it is the same thing of a vector space as the note, as in your note, but in a slightly different way, but it is more understandable, right? So up to now it is clear. I think I'm not going to like describe those two laws, and it is just a matter of reading and what is those 10 rules are, right? So is it clear? Hello? 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 Is it fine, or you need to more have another clarification? Okay. So the another thing is, because I said that because there's a key different, I need to extract here. Let's say you have get some, let's say 3 vectors. This we call a set, right? Set of vectors. It means we take 3 vectors and notate that as a group or some set, and this is set of vectors. But this is not a vector space, right? It means set of vectors and vector space is a two different things. Set of vectors is some collection of vectors. That's it. It is a set of vectors. You get some vectors and you denote that a set. It is a set of vectors. But vector space is not only just a set of vectors. It has to satisfy that rules in order to become a vector space. That's the key difference. So also by having this in mind, we define something we called subspace. Let's say subspace, I denote it as W or something. If it is a subspace, let's say if we consider this as a set, right? If we consider this as a set, the set of vectors that belong to this subspace should be a subset of V. It means if you have original vector space V, your subspace vectors, if you consider this as a set, it should be a subset of your original vector subspace. Also, if in order to become W a subspace, this should have these properties. It means A plus B in W, where for all A and B inside W, also KA inside W. It means this is K is a scalar, right? It means if you take a subset of your vector space as a set and it satisfies these closure properties with respect to your addition and scalar multiplication, it is what you call a subspace, right? So I just denote these two terms. There's nothing much to worry about these two terms. Only thing you have to know is the only difference of set of vectors and the vector spaces, there need to be some criterion to satisfy of the vector spaces. Okay, so these are just, let's say, some sort of rules or definitions. You cannot say why this is true because it is the way it is defined. So using these things, we have to identify some sort of algebraic things in vector spaces. That's what we are going in the linear algebra module. We have to deal with matrices and we have to deal with the basis sets and the spanning sets and all other things. Up to now, is it clear? Because this only thing is you need to realize, because this nothing much to memorize. Only thing you have to understand is, if you take, say, set of vectors, it is different from a vector space. Vector space is one thing, set of vectors is one other thing. If you understand that thing, that is totally fine, right? You got it? Hello? Hello? Fine? Or you need more clear understanding? Or you need more explanation? Please let me know, right? Is it clear? It is not like a theoretical subject. I just like give you some introduction to the vector spaces, right? Nothing more than that. Hello? Okay. So then we will go back to some basic idea of what is a basis, right? So before going to the basis, I need to go with some linear combination. It is just an idea. Let's say you have some n vectors. Let's say v1, v2, and va. We call, let's say I get some vector v. It is, let's say, a1, v1, a2, v2, plus into an, vn. This type of thing, these a1s to an are real numbers. If you take, it means you take some set of vectors and you multiply it with some scalar quantities and then you add up. This type of thing you can call it as a linear combination. It means it is a linear, right? You only have real coefficients or like scalar coefficient to your vectors, and you have add some summation, because this is itself a vector, this is itself a vector, and this is itself a vector. So if you add this up, what you get is resulting as a vector, which is of course a linear combination of the vectors, which is we call a linear combination of vectors. Okay. Now we have the with this idea in mind, we define something called basis of a vector space. This part is really important, right? Okay. Let's say I denote this is my vector space. This is my vector space. It is obvious that you have infinite number of vectors in this vector space. It means you cannot count the element in this vector space, because if you take any two vectors, if it is now empty, the addition of these two vectors also in this vector space, so you can have infinite number of vector spaces inside your vector space. In the basis, what we're going to do is, the basis is some set of vectors, right? Let's say I denote as b1, b2, and into, let's say, some bn, capital N. It is some set of vectors. It has some interesting property, right? Basis is just some set of vectors. The basis is let's say if we take any vector from this vector space, let's say it is something called W or something. If you take any vector, you can express this as some A1 B1 times A2 B2 times into AN B capital A. It means if you take a basis set, you should be able to represent any vector in your vector space as a linear combination of your basis vectors. Okay, you can have any amount of numbers in your basis, but if you can represent any vector inside your vector space using these basis vectors, you call it as a basis set of your vectors or basis for your vector space. Basis for V. It means if you take any vector V, you can decompose into a certain part of your vectors. Okay, it means you have set of n vectors, and using those n vectors, you can represent any vector inside your vector space using as a linear combination. So there's two natural questions, right? It means first, how to find this AI? How to find A1 to AN. Okay, there's one question, how to find this A1 and AN, and number two, how to verify basis. Okay, those two questions we need to answer, right? These are actually the basic concepts we're going to learn when regarding going to the basics, right? If you take some basis, if it is any other vector, I'm not telling it is a geometrical vector, let's say it is something, it can be something like this. Okay, there's certain components, or it can be something like function or anything, but it is inside your vector space, some object, but you can represent it as a linear combination of these basis vectors, and then you call it as a basis. Also, there's another idea called the dimension. This is the minimum number of vectors required in basis, for basis. Let's say I explain this as using an example. Let's say I get my 3D vector space. Okay, this is a vector space. It means this is nothing but, you can denote this as V, something like V1, V2, and V3, where V1, V2, and V3 are real numbers. It means this is denoting as your vector has three components. Each of component is a real number. So using this case, you can easily find our we call, I write some basis for this. I can write some three vectors as basis. Let's say I write E1 as 1, 0, 0. E2, we call it as 0, 0, 1, 0. And also E3 as 0, 0, 1. Because I can take this as a basis. I just write a very simple example, right? Because I have vector with three components, which are real numbers, and I take another three of these vectors, which has a basis for my vector set. Why it is to be true? Let's say any vector in this vector space, let's say I have any vector, I can written in this form, right? Has three components. I can write this vector as exactly as something like this. Plus V2, 0, 1, 0, plus V3, 0, 0, 1. You can easily see, if you scalar multiply these vectors and add them up, you will get this vector. These three coefficients, right? We usually call it as coordinates. It's nothing but it indicates how much proportion of your vector is belong to that basis vector. Usually we call these three vectors, or this type of vectors, we call standard basis, right? It means if you have n-dimensional vector, you can have actually component up to n, right? Up to n components, you have 100 or 1000 or any of the number of components you can have. This type of set of basis vectors you call it as a standard basis. It means you take 1, 0, 0, and you take 0, 1, and also in this type of set of vectors, you just call it as a like standard basis for your vector space. It means it is the just standard. That's what we use. Let's say if I take my 3D coordinates, Z, y, x. If I take any point, let's say x, y, z, I can treat this as x, y, z, z coordinates as my, if I take the position vector, let's say r, I can write it as r equals x, y, z. In simple mathematics, you know that. So this x, y, z, we call coordinate in our coordinate geometry. It is actually nothing but the coordinates relating to these standard basis vectors. Okay. So it is actually standard basis. Also in R3, the dimension is 3. You need to have minimum of 3 vectors to represent your vector. The reason actually, the reason I explained with matrix algebra in later, right? So if you have R3 or Rn, you need to have at least three vectors, or it is n dimensional, you need to have n vectors to represent. If you have, let's say, because if you know R3 is 3D, it means 3 dimensions. 3 dimension or dimension is 3 means you need to have at least 3 vectors to represent your vector space. So in up to this point, you need to understand what a basis is. You don't need to think about much about the dimension. You need to think about what a basis is. It means you take any vector space, you can find a set of vectors which can use to represent any vector in your vector space as a linear combination of those vectors. And also the coefficient of these vectors, if you write it as an expression, you call it as a coordinates. These are pretty much useful in vector transformations. Up to now, it is clear? Hello? Is it fine? Or do you need more like clarification for these vectors? I'm not using any of the symbols. I just want to give you the idea, right? Because if you find some problem, you can easily answer that problem using these using these concepts, right? Do you understand what a basis is, or you need more clarification? If anyone has question, you can ask now. Hello? Or I am too fast, you can just drop me a private message and tell, yeah, it is, you are too fast, or you want to say it in public. That I don't mind at all, right? Hello? Is it fine? Or yeah, like don't be afraid to like unmute your mics, right? So it is better, because now if it happens like I'm get boring, right? Because I'm just talking to a computer screen, I don't hear nothing. And okay, now you know what is a basis is. Now you are telling her, what the hell is that? Why the hell we learn this stuff? Okay, now I am going to introduce some example of real application of these concepts, and which can be tested in your exam as well, right? Okay, let's say I take some matrix. Let's say some arbitrary numbers, 5, 1, 3, 8, 4, let's say 7, 9, 8 or something. And you take x1, x2, x3, right? And let's say you have equivalent to this is, actually I just write this, right? I don't know whether it's solvable or not, right? Let's say this is equivalent to 5, 6, 9 or something, right? I don't know. I don't know if it is solvable or not. So I just write this. So if you solve this out, you can, if I consider this part, right? If I consider this part, I can expand this as, let's say, 2x1 plus 5x2 plus x3. This is the resulting, it's a vector, right? This is actually 3x1 plus 8x2 plus 4x3. And it is 7x1 plus 9x2 plus 8x3. Now I do some slight modification. Right? I do some crazy thing here. I get x1 out and I have 2, 3, 7. I write it as a column vector, right? Plus x2 times, I write this as 5, 8, 9. And I write this as x3 times 1, 4, 8. You know how to multiply scalar multiplication. And if you multiply this vector, you would get, actually, you would get 2x1, 3x1 plus 7x1. You get this vector. And you have to add, if you multiply this one, you will get 5x1 and 8x2 plus 9x2. And you have to get x3, 4x3, 8x3. These are three vectors, and if you add them up, you will get this vector. Now carefully look, what does thing is look like, right? You can easily see these are the column of these vectors, right? Because this column is here, this column is here, this column is here. Now, if you treat this as coordinates, what would happen? What would happen? What happen is you can change x1, x2, and x3. You treat it as coordinates, and you will get a vector set, and which is of course the vector set which can be expanded by the basis of these two vectors. It means you have 2, 3, 7, one vector. It is 5, 8, 9, and 1, 4, 8. It means if you can change x1, x2, and x3, then you can get any linear combination of these three vectors, three column vectors. It means if you see something like this, this is nothing but the result of this vector space or this matrix product. It means you have all possible vectors that you can get. This kind of product is nothing but the column space or the vector space spanned by these three column vectors, which is in fact we call the column space. Do you understand how the idea of the basis vectors and the linear combinations can be brought into this matrix multiplication? If not, please tell me. Yeah, I don't understand. Okay, please tell me. Hello, do you get it? Hello. Okay, so it means you have the column space, which your column space, because typically we call it as a column space. Or if you consider some vector product something like this, let's say x1, x2, x3, and some vector product something like this. Let's say you have some numbers 1, 2, 3, 5, 6, 9, or 8, 4, 2, or something like this. So in this case, actually, you would get, in fact, you would get row space, right? I'm not going to write, because in that case, you get linear combination of these three vectors. You can clearly see you get some vector multiplication, something like this. You would get some row vector, something like this: x1 plus 5x2 plus 8x3 and 2x1 plus 6x2 plus 9x3, comma, and 8x1 plus 3x1 plus 9x2. I think I messed it up, right? 2x1, 6x2. Oh, it is correct. This is 4. And this is actually nothing but 3x1 plus 9x2 plus 2x3, right? So you can decompose it to actually x1 times 1 plus x1 plus, you can actually even have 1, 2, 3 plus x2 times 5, 6, 9 plus x3 into 8, 4, 2. Okay, so this is actually nothing but the rows of your matrix, and these are you can treat as coordinates, and then you will get all vectors which can be think as a combination of your rows, which is we call the row space. Okay, so this is how, because this is why actually the linear algebra and vectors have to deal so much, because you can think as a matrix as a collection of vectors, either collection of row vectors or either collection of column vectors, and use that insight to solve and analyze how your linear systems or linear systems of equations have solutions or not having solutions, or what are the nature of the solutions. You can easily analyze using the nature, the behavior of the vectors. Do you understand how these two things are connected? Is it fine, or do you need me to get another understanding, another explanation on that? Because this can be tested, right? This clearly tested. You can simply ask, what are the dimension of the column space? I come to that next. Okay, what is the dimension of the column space? What is the dimension of the row space? What is the null space? Anything you can if you can properly answer if you know this thing correctly. If you get this thing, hello, the only thing you have to is the product is this product or this product. In this case, we have column vector. In other case, you have a row vector. In each case, you get either a linear combination of your column vectors or this type of vectors or your row vectors. Understand, or do you need another explanation on that? Hello? Do you have any problem? Please ask, right? I'm not going into, because if you understand this thing properly, then you have actually you can understand linear transformation with no problem, right? And the only different thing coming into the Gamsik procedure, I will explain in the similar manner. Then you can do any problem without memorizing single thing, right? You only have to memorize the 10 rules of the what is the vector space is. That's it. You all need to have remember, and then you can do anything with vectors, because you need to have to see this connection. If you see this connection, there's nothing to do in this module. Straight away plus, right? If you don't see, actually this is a mess, right? The only thing you have to think about is you have to be in this inside, right? Because these things can be tested. Is it fine, or you need to have more explanation on that? Hello? 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 Fine. I just have to copy this because I need to provide one more explanation on that, right? Before going into the next part. Do you get anything to clarify? Okay. I don't, there's not, I think you guys are silent. Please don't afraid to ask anything, right? I'm not going to bully you or laugh at you, right? Because I think, because everyone is not knowing anything, right? So everywhere I say I'm not very good fluent at electronics. Yeah, that's the correct thing, right? You got the point, is so correct. If you get this matrix multiplication, what you have this says as a vector, right? If you consider this all possible vectors, very good question. I feel like answer those type of questions, right? All possible, let's say because this matrix is fixed, right? This matrix is fixed. You can vary x1, x2, and x3. Forget about this equation part, right? Forget about this thing. You can, if you consider this part, you can change x1, x2, and x3, and you can have infinite number of resulting vectors using this product. This product is in fact all the linear combination of these three vectors. In fact, if you set x1, x2, x3 to 0, you get 0 vector as well. It means you can have a vector space which can be spanned from these three vectors. We usually called a basis spans vector space. Spans means nothing but the all of the linear combination of these basis vectors, which gives us a vector space. So if you consider those column vectors, these are acting as a basis for a column space. So particular column space of this matrix. If you consider rows, those who are acting as a basis for the row space. Okay. The two words is, if you consider these three columns and take it as basis vectors, you can get the column space. And if you take these three vectors and take as these three vectors as basis and get a vector space from that basis vectors, you get a row space. The two words coming from that, whether you consider your columns as vectors or rows as vectors, because you can think in two ways a matrix, right? You can think of it as a collection of columns or collection of rows. Fine. I think the one who asked that question got the correct answer, right? You got the point correct, right? That's what I need to highlight here. There's no difference between a matrix product and a basis set and a vector space. This is the important thing in linear algebra module, right? If you consider linear algebra, you deal with linear systems of equations, but you use the concept in vectors to simplify this because of this relation. Because any linear system of equations, you can think of it as a vector space which is spanned by some basis vectors, which can be rows or columns of a particular matrix. You got my point? Or the one who asked? Okay. So if you have any question, please drop one in the chat. So now the other question is, now you know all the possible outcomes. If you put x1 and x2 to these values, you get a vector space. Now what you can think about, now clearly I give you some minute to think about, but if you spot this correctly, I think you can do any linear systems problem pretty much easily, because you know the concept. Let's say I need to solve this system. It means I need to find x1 and x2 and x3 values, which gives the output of this product as 5, 6, 9 vector. So it means, what does this mean? Or if it means there can be two things, right? I can either have a solution or I can not have a solution. These two things, okay? These two things, what does these two things mean? Before going into how to find whether this has a solution or not, you need to understand what does it mean this system of equation has a solution. What does it mean? Hello? What does it mean? Okay. So it means that, let's say, you know, the expansion of these vectors, you can write this as 2x1 plus 5x2 plus x3, right? And also you have 3x1 and 8x2 plus 4x3. And also we have 7x1 plus 9x2 plus 8x3. It means if you take this vector, correct, exactly, 5, 6, 9, this vector. It means if you consider the vector spanned by these three basis vectors, if that vector space contains this vector 5, 6, 9, this system has a solution. But if it doesn't, what will happen? This vector space, let's say I did not test some sort of thing. This is the vector space spanned by these three basis vectors. Okay. What will happen? This vector space does not contain this vector. It means you cannot have x1, x2, and x3 value, or you cannot have a linear combination of these three column vectors which gives this vector. It means you have no solution. So in linear system, whether we have a solution or not depends on the right hand side of our equation is inside our column space or not. Okay, did you get my point? Hello? Fine? Hello? Okay. So then, okay, then we can define, let's say, I think we can have, okay, so, okay. So this in the basis, I think you have to be on any number of these things. And okay, so, okay, so there's two different things you need to know. I think two words. I will explain that. I think I mess up the word with basis. I will explain it later. So then this is the vector. So you need to find out if this column space contain this vector or not. Okay. Okay. So I tell about, you have vector space. Now you have know some things, right? You can have a basis set. Basis set is nothing but a set of vectors that can span this set. Actually, vectors that can span this, and also some another condition you need to satisfy. Let's say this is as b1 and b2. These vectors should be linearly independent. It means if you write this equation, let's say a1 b1 vector plus a2 b2 vector plus a capital N b capital N vector is the number of basis vectors equal to 0 vector. This holds if and only if a1, a2, and an all are equivalent to 0. If this condition happened, right? If this condition happened, we call this set is linearly independent. Also, there's one thing to memorize. All basis set have same number of vectors. Let's say I write some simple example. Let's say I take R3. I can have easily 1, 0, 0, my standard basis. And also I can have, let's say I can have 0, 1. I can have this vector as a basis. Also I can have 0, 0, 1, 0, 1, 1, 1, 1, 1. Okay. I can have these three vectors also as a linear, because these two are linear independent, right? Because linear independent means you cannot express, let's say you have these three vectors are linearly independent, means you cannot express any of these vectors using the other vectors. Let's say you have b1, b2 into bn vectors, and you take b1 vector. If you can express this b1 vector is some combination of b2 to bn vectors, this is not linearly independent. It means you cannot represent one vector in terms of another vectors of that set. We call that set of vectors are linearly independent. So in that case, actually you can have infinite number of bases for particular vector space, but the common thing between all basis sets are they all should contain same number of basis vectors. Let's say if you take R3, all set of basis vectors should contain 3 vectors, nothing more than that. Also you can have some set like that. Let's say 1, 0 and 0, 0, 1. This, and also you can have some arbitrary vector like this. Also using these 4 vectors, you can express any 3-dimensional vector using a linear combination of these 4 vectors, because these are 4 vectors. In such a case, we call such a set as a spanning set. Spanning set can contain any number of vectors. Previously, I mistake about the basis vector. Actually, a spanning set is you can contain any number of vectors in the spanning set that can because it's only requirement for spanning set is you should be able to represent any vector in your vector space as a linear combination of one or more vectors in your spanning set. To be a basis, you need to to be a spanning set of basis, you need to have linear independent condition. It means you have some spanning set which is also linearly independent. You have a basis. Also, number of vectors in your basis set, it is a constant through all basis vector sets. You call it as a dimension of your vector set. Fine. Hello. You got my point? Hello. 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 Did you get one? Okay, linear dependent. Okay, I will show you a linear dependent set. I get some this example as well. Let's say 0, 0, 1, 0, 1, 0. Let's say 0, 1, 0, 0. And I take 1, 2, 0, something like that. I clearly see I can express this thing as 1 times 1, 0, 0 plus 2 times 0, 1, 0. Okay. It means using these two vectors, I can express this vector. So if you consider these 4 vectors are not linearly independent. Okay. Also, if I write the condition, it is A1, 0, 0, 1 plus A2, 0, 1, 0. I will for more robust way next to you. I just show it an example why it is to be the condition is true, right? 1, 0 and 0 and plus A4 and 1, 2, 0, 0. And you can put A4 equals -1, A2 equals 2, A3 equals 1, and A1 equals 0. If you put these 4 values, which satisfy this equation, because if you put this -1 here and you put 1, 2 and 1 here, you will get exactly same vector, but in the opposite of sign here, because if you add this up with substituting this 2 and 1, you will get 1, 2, 0 vector as before. But if you put -1 here, you get cancelled out and you get a 0 vector here. And you put 0 to here, get a 0 vector here. And 0 vector plus 0 vector, it is a 0 vector. But you have a solution now, this satisfying, what will happen, satisfying, which is not this, right? It is not all variables equal to 0, right? This is not the solution. You have some other solution than this to this equation. So this set is not linearly independent. So Spanish set doesn't need to have linear independence, but the basis should have linear independence. Yes, correct. Previously, I forgot to mention that, right? I just forgot the word. Okay. Basis should have linear independence, but spanning set don't need to have linear independence. It can have, actually you can have 100 number of vectors, but the spanning set should have more than the dimension. Let's say your dimension is 3, your spanning set should have 3 or more vectors. It cannot have 2 vectors, right? It should have either 3 or more vectors. Okay, because otherwise if it is have 2 vectors, it is not a basis even, right? Hello, fine. So it means the dimension is the minimum vectors that you need to inside your spanning set or the number of vectors in your basis. Okay, the basis set is the minimum number of set which having the minimum number of vectors that can be spanned your vector space. Okay, you got the point? Hello, fine. Hello, hello, hello. You got my point? Okay. Now, before going into much further, let's consider other case as well, right? Let's say we got, let's say some vector 5, 5, 1, 6, 6, 9, 8. And let's say it is x1, x2, x3. This is equal, let's say 6, 9, 8. Okay. Now what if, right? Now what if you take these 3 basis vectors, these 3 columns are linearly independent. Just think, right? What if these 3 columns are linearly independent? What would happen? If these 3 columns are linearly independent, your dimension of your column space becomes 3. It means you have 3 vectors, and in particular, you have this is a R cubed one here. So it means you have 3 vectors which have 3 components. It actually this each vector is belonging to R cubed. It means your 3-dimensional vector space, because you can consider alone vectors. It is 2, 1, 9 or 1, 5, 6 or 5, 6, 8. It all are independently belong to the 3-dimensional vector space, because if you consider just as a vector with a standard basis. So these 3 vectors are linearly independent. This can span R cubed. It means this can represent any vector belong to R3 using some x1, x2, and x3. It means it doesn't matter what my right hand side did, it's always going to be R in my R3. I can represent my right hand side using some linear combination of using these 3 vectors. You got the point? It means I have 3 vectors. If these 3 are linearly independent, what will happen is my right hand side always going to be true. It means it is going to span cube R3, right? The columns are going to span my whole vector space. Did you get the point? Hello, fine. Hello, you got the idea of the independence, because these are 3. You have in vector, you have 3 components, right? You have dimension 3 means you can represent any vector using 3-dimensional vector space, because it can span any number of vectors. I will explain in other terms as well. Okay. Let me check. I can find a good problem here. Okay. I can have some problem here, right? Okay. Okay. I will explain something. I need to find a problem, but let's say you know how to find the solution of this metric space. What I use is Gaussian elimination. Okay, so do you need to revise it to using Gaussian elimination? I think this was done in first semester, but if you want, I can remind it as well. If you want, just drop me a chat. I will go through step by step what need to have done and give you some proper understanding as well. What is actually Gaussian elimination means, right? it is, you may see it as some vector operations or matrix operation, but it is not actually, it is something we would do. Okay. So, okay, can you please tell me some linear, okay, I will Google some question as well. Linear systems. Otherwise, if I get a solution with no solutions, that will be a disaster. System of equations. Let me check. Because it is better to have. Okay. I just quickly Google a problem and okay. I just get two equations, right? I get 3x minus y equals 7 and 2x plus y. Actually, I have to do more than that, right? So I think this should be okay. Wait a minute. I will. Okay, I will show you more than one variable. Otherwise, it will be disaster. 3x minus y plus 3z, it is equivalent to, let's say, 10, and 2x plus y plus z equivalent to 9. Then I think the solution would be 3 and 2, right? Let's say x plus y plus z equivalent to 6. These are my three equations, right? So I just get the solution system of what equation has. So only thing you have to do is you can represent this in matrix form. Let's say it is in matrix form. You have to forget about the variables. Just write the coefficients. This is enough, right? 2, 1, 1, and 1, 1, 1. This is nothing but what we have to did it other case, right? And we have get x, y, z, and then you have 10, 9, 6. Okay. Then you can write something called augmented matrix. You have to write 3 minus 1, 3, and draw some line, and you put your right hand side here. Then 2, 1, 1, 1, 1, 1. Okay. Then what you're gonna do is you're gonna call something, you're gonna do something called row operations. Before that, what you're gonna do is do something called pivoting, right? So first you need to do is you start with this column and you're trying to make this coefficient 1, right? So if you need to make this coefficient 1, you need to divide the whole row by 3. It means in this case you can do, if I denote it as any row is row j, you can divide it by any positive or negative real number. Also, you can add or subtract any other row to that particular column, treating them as vectors. So first thing I need to do is, actually I'm going to do is, I consider my first row and I'm going to divide it by 3. Then I can write is 1 minus 1 over 3, 1, 10 over 3, and other parts is not different. 2, 1, 1, and 1, 1, 1. It is 9 and 6. Okay. So you can have this. Then what you have to do is, if you doing this one, you have to do, if you make this one, you have to make these two things are 0. Okay. So to do that, what you're going to do is, you using this row, you can take this row 2 and you can subtract 2 times row 1, because this has 1. If you need to make this 0, you need to multiply this by 2 and subtract. Okay. So then also you need to have in your R3, you have to just subtract your R1, because 1 minus 1 is 0. Then you have to compute the other values. So in this case, you have 1, 0, 0. And here you have minus 1 over 3rd. And here you can have, if you multiply minus 1, if you subtract 1, subtract minus 1/3 from 1, you would get 5 over 3, right? So then here you will get minus 1, and this 1, and this is 10. And here you would get 9 minus 20 over 3 means you would get 27, 7 over 3. Okay, you would get 7 over 3. And then the third row, you would get 4 over 3, 0. And you would get 6 over 6 minus 3 over 10, 3 over 10 means actually it is 18, and it is 8 over 3. And you can do like this, and then you need to have make this thing is 0, this thing as 1, and this is 0, and then finally you have to make this 0 and this 1. Okay, so you need to have perform all the row operations. Once you've done that, once you actually do one thing, something, make this 1 and make this 0, actually you can forget this row. Then you can only considering this part and consider row operations, because these are zeros, so nothing much happens. So you, to make this one, you need to divide this row by this number, and you get this 1, and you need to perform another operation to make this indices is 0. So then you will end up as your Gaussian elimination method. This is nothing but what happened. What we do when we actually when we doing is, you will have something like this: 1 0 0, and you have some right hand side, and 0 1 0 0 0 1. This is the one you should have if you have a solution, right? Because always this will be not the case, right? It is sometimes you can have all zeros rows as well. I will explain that later. So what will happen is, if you write in this form in this matrix, this is, you can write the reduce your equation form. Let's say this is B1, B2, and B3. You can reduce your equation form as 1 0 0 0 1 0 0 0 1 as x1, x2, x3 as B1, B2, B3. And then you can have x1 equals B1, x2 equals B2, and so on. This is nothing but what you're going to do if you consider these three simultaneous equations. You need to only have x. You only need to have x in this equation, and you only need to have y in this equation, and you only need to going to have z in this equation. And what you're going to do, if you consider these two equations as a parallel set of equations, and you add and subtract from each and every equation to make this happen. It means you need to only have x. Means here what you need to have first, you have to make this coefficient 1, you have to divide by 3, then you need to remove y and sorry, I got it wrong. Okay, so here it is not something like this, right? It is going to be something like, not like this, it is something like this. It will happen, you have something here, it not necessarily need to be 0, this is 1, and we have something here, and then you can have something here. Then you can have actually some coefficient here, some coefficient here, some coefficient here. So you can have x1 plus some coefficient, x2 plus x3, and you can have your answer, right? So this type of thing you can have. It means in the last row you can only have one variable. This is nothing but what you're going to do is, you make the coefficient of x is 1 in this equation, and you remove x from other two equations. And then in this equation, you make y's coefficient 1 and remove y from the third equation. When you move downwards, you drop one variable one by one. So at the end, what you have one equation with one variable, you can easily get the solution. Then let's say you can have if you left with this kind of equation, let's say x1 plus 2y, so x plus 2y plus z equals something, and y plus 3z plus something, and z equals something. This type of thing that you can have at them. So if you know the value of z, you can easily calculate the value of y. If you know y and z, you can easily calculate the value of x using the first equation, using this reduced form. This is what we call the Gaussian elimination. I will send you some video regarding this. It's not much difficult, but only thing you know, you rearrange this equation, because if you take an equation, you can divide both sides of this equation with the same number. Also, you can add and subtract from each and every equation. So instead of taking these three as rows, treat this as the equation. This is in fact the equation without the coefficients, without the variables, right? So you need to have some sort of this form, right? 1, if in first row you have to be first element is 1, and other in first column first element should be 1 and other element should be 0. In second column second element should be 1 and the other element should be 0. And sorry, in here, right? And in the third element, your elements above in the third element should be 1 and elements above can take anything, but if you have any element below, these two are these elements should be 0. Okay, the form is nothing but something like this. Let's say if you take any variable, in the result you should have 1 something 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 and 0 1 something something 0 0 1 something 0 0 0 1. Okay, it means you can have this is actually, if you take this as a matrix, right? If you draw a diagonal like this, let's say this part can only contain values not equal to 0. But if you consider the part below diagonal, this all should contain 0. This cannot contain any non-zero value. Okay, fine. Hello, is it fine? Hello. Okay, so I'm not going to do Gaussian elimination much, but I need to give you some insight before, after you do, what will you get after the Gaussian elimination. Let's say after the Gaussian elimination, let's say you have n rows and you have something like this. If you get main diagonal, your main diagonal are all 1, right? N rows all 1, and you these parts you have 0. It means you have n ones, n leading ones, right? Those are the one we called actually leading ones, because the elements before these elements in the rows before these ones are all 0. So we call these are leading ones. If you have n leading ones, it means you have leading ones. Number of leading ones are equivalent to the number of rows. You have a unique solution. Unique solution, it means number of leading ones equivalent to number of rows or number of equations. If you have number of leading ones less than or equal, sorry, less than number of rows, you have infinite number of solutions. Okay, you have infinite number of solutions. It means you have number of leading ones less than n, and you have infinite number of solution. But let's say because this is some other condition satisfied, let's say you have n and up to m rows you have leading ones, let's say 1 1 1. In other case you have all zeros here in your left hand side. Okay, if you have infinite number of solution, if the items below this level of your right hand side should also contain 0, then you have infinite number of solutions. But if you contain non-zero values below that level in your right hand side, this system doesn't have any solution. Okay, the system cannot have a solution satisfying all the equations. It means, let's say you have 4 rows, let's say 4 rows, I write, let's say you have something like this 1 2, this is your right hand side, 3, right? So then you have 1 0 5. Okay, let's say it is 9 6 1, and these are all zeros. Then what would happen? This row is all zeros, but this part is non-zero. Then you have no solution. But if this part is also 0, you have infinite number of solutions. Because if this is 0 means this last equation becomes, if it is non-zero value, it becomes 0 equals 1. So this cannot be happen. Because in this equation you can have, if you multiply this, if you get this equation, it is 1 2 3 0 1 5. After Gaussian elimination, if something like this, x y z, something like this, is equal 9 6 1 or something, let's say. So in last equation, what you get, if the first two equation it doesn't matter, but the last equation it will get 0 equals 1. So this cannot be happen. So this system cannot have a solution. So to have a solution, if a row doesn't have a leading one, all the element of that row should be equivalent to 0. So actually you can learn more this as Gaussian elimination. I will share you a video and or not on that, because it is just a technique that we use to solve the equations. Okay, you got that point, or you need to do more explanation on that, how it comes or not, because I'm not going to pretty much depth on that because we need to have very limited time about this. To remind it, what is the Gaussian elimination is? Hello? Do you find it that, or I need to explain a bit more? Because I know it is quite fast, but if I get more detail, we will be less time to investigate on that. You got the point? The solution of the solution and this case. Also, the number of leading ones. Actually, number of leading ones also equivalent to the dimension of your column space. Column space also, let's say in this case, another thing you have to remember, after you perform a Gaussian elimination, number of leading ones is equivalent to dimension of column space as well as dimension of row space, because dimension of the column space and the row space are equal. Okay, so then also now view that, right? Because you can perform the Gaussian elimination and you can count the number of leading ones and you can get the dimension of the column space. Okay, if the dimension of the column space is equivalent to the number of equations, let's say I denote this as 1, this is a matrix and this is your x vector, or let's denote you have some matrix and you have some x values, x2 and some x values, and you have some right hand side. If this condition happens, dimension of your column space is equivalent to the number of equations for any right hand side, you have a solution. Okay, for any right hand side you have a solution. Also, in linear equations there is something called a null space. Okay, it means, let's say you have something value like this, let's say it's 1 2 4 and you got 0 1 1 and you got 1 3 5 and you got x1 x2 x3, and then you have in the right hand side you equal all to 0. The null space is nothing but the set of vectors or the vector space that each vector in that vector space, if you substitute into this x1 x2 and x3, what will happen in your right hand side, you give a 0. It means, in other words, the solution set of this equation, which we call a null space. Okay, so the null space, we have to get a solution, we have to perform the Gaussian elimination again on these equations, and I just take this as some count example. So then you can perform Gaussian elimination something like this: 1 2 4 and 0 1 1 and 1 3 5, and these are all zeros. You can easily see that this has a leading one and this column has a leading one. The only thing is we need to remove is this one and this 3. So what I need to do is I'm going to remove R3, I'm going to subtract R1 from it. So then I can have 1 2 4, this is not different, 0 1 1, and this becomes 0, and this becomes 1, and this becomes 1, and this becomes 0, right? This becomes 0. Then you can easily see that if you remove, you need to make, if you want to make this 0, because you need to make this 0 to make this a leading one if possible. If you remove, if you need to do that, you have to remove R3 from R2. Then what would happen? You will end up something like this: 1 2 4 1 1 0 0 0, and you have 0 0 here. Now you have two equations. You can always treat this as a column. This column is with respect to x, this is with respect to y, and this with respect to c. Okay, so then you have equations: x plus 2y plus 4z equal to 0, y plus c equivalent to 0, and then you can have here you can have 0 equal to 0. It is actually no use. Now you have three variables
two equations. To solve this type of equation, what we do is we assign some parameter to one of the variables. T is a parameter. Then if we assign one parameter to a variable, then our number of variables, after that, our number of variables are only is x and y. We are going to find x and y in terms of C. C, or in other words, T, right? Because we assign Z equals T. Then we can have this one, these two. From 2, we can have y equals minus T. And from 1, we can have x minus 2t plus 4t equals 0. So then we can have x equals minus 2t. Then we can have x, y, c vector. In terms of t, we can write minus 2t minus t and plus t. Then we can take t out. We can write this as minus t, t times minus 2 minus 1 and plus 1. It means if we put any t value to this, let's say t equals 1, you get minus 2 minus 1 and 1. This vector also satisfies these two equations, or this set of equations. Let's say this original equation set is x plus 2y plus 4z equal to 0, x plus y equal to 0, and x plus 3y plus 5z equal to 0. These are my original equations. If you plug back into this solution, if t equals 1, and plug back into my original set of equations, these three equations, it will satisfy the original equations. If I put t equals 5, also that vector satisfy the my set of equations. It means to satisfy these three equations, I have infinite number of solutions, because the number of leading ones is less than my number of rows, as well as the all other rows are zeros. But if this doesn't happen, if this is 1, or let's say any other non-zero value, say 5 or anything, right? If this value is not equivalent to 0, doing this is not possible, because last equation becomes a contradiction. Okay, hello, fine. That is we call actually a null space. There's some pretty much relation. You call it also, if you take a null space, sometimes you can have something like this. If you end up, let's say, sometimes you can end up some equations like this. I just write this one. Let's say x1 plus 2y plus 3z plus w equal to 1, and you have only left with this equation. So then you have to get three parameters. Let's say z equals w and z equals u, v, and w equals t. You have to take three parameters, because you have only one equation, and all you have four variables and one equation. Okay, it means you have, let's say you have some set of equations, let's say 4 equations or anything with four variables. After perform Gaussian elimination, you only left with one equation. Then you have to assign 3 parameters to your variables. Then you will get x equals minus 2u minus 3v minus 3t, sorry, minus t. Okay, then you can write your solution x, y, z, w. We can write this solution as minus 2u minus 3v minus t, and this is u, v, t. You can write this as, let's say, take u out. You can write minus 2, 1, 0, 0. Take v out. You can write minus 3, 0, 1, 0. You can take t out. You can write minus 1, 0, 0, 1. Okay, so then what you can have, you have 3 basis variables, and you have 3 vectors and 3 coefficients. These are coefficients. You have 3 basis vectors. It means you can take any v, u, v, and t value which result a solution vector, which is a solution to a set of your equations. In such a case, your dimension of your null space is equivalent to 3, because you have 3 linearly independent vectors. You can clearly see that these 3 vectors are linearly independent, because none of these vectors cannot be expressed as other vectors, because usually after Gaussian elimination you will get linearly independent equations. Otherwise, there's no point taking these 3 as independent parameters. Okay, so then this is we called as another term we use this as is a nullity. Nullity is nothing but the dimension of your null space. Also, we called some sort of range. Range is nothing but dimension of your column space, right? Dimension of your column space. Okay, so there's a theorem, your range plus nullity equivalent to your number of rows, right, on your set of equations. It means your dimension of your null space and your dimension of your column space, if you add them up, you should have the number of rows in your equation system. Okay, no, it's number of rows. You should have number of columns, right? Number of columns. Okay, number of columns. Okay, so not number of rows, you should have number of columns. Yeah, number of variables. Okay, it means the dimension of the column space and the dimension of the let me check back and see. I think it should be yeah, I think it should be right. Yeah, it should be number of columns, right? Not number of rows, number of columns. You should have a number of columns. If you add the dimension of your null space and the dimension of your column space, if you add those numbers together, you should have the number of columns, or in other words, number of variables in your set of equations. Okay, so this is a theorem. So it is there's nothing to worry about to prove that theorem. So up to that point is clear? Hello? Fine, or you need any other explanation? Hello? Hello? Okay, so okay, if it is not it's there's not a problem, I will go to another problem. It is nothing but you have to remember, it means if you have some set of equations, you have right hand is all zeros. If you find some solutions and you get a solution family or linear combination of some vectors as a solution, the dimension of this vector space you call it as a nullity or a dimension of your null space. And range is, I think I don't sure about this word range, right? Range is nothing but the dimension of your column space. Actually, I will check back and see. I don't sure about which. Just say it is a dimension of your column space, right? Dimension of your column space. And if you take those two numbers and add them up, you should have the number of columns or number of variables in your equation set. Okay. Now we are going into another thing called inner product. Okay. So I just give you some brief idea about what is the inner product is. This is nothing but some operations on vectors. Okay. Also, this should satisfy following criteria. I just write, let's say A or B are two vectors, and this satisfies this property. We typically denote inner product as something like this, right? I treat this as actually this inner product is a real number, right? Otherwise, if it is some field, it is going to complex. But in your module also, it is as a real number, right? In 2 also, we can have A plus B into C. It is equivalent to A into B, so A into C.
into A into B into C. Okay. So then also you can have A to A also greater than or equivalent to 0 and A equivalent to A equals 0 if and only if A equivalent to 0 vector. Again, it means you have inner product. There's nothing much that let's say the simple inner product we know is nothing but our dot product, right? Let's say dot product. Let's say you have taken some vector like 1, 1, 1, and B is nothing but let's say it is 1, 1, 2. So generality 1, 3, 1. And if you take the dot product between these three vectors, you would get 1 times 1 is 1, 1 times 3 is 3, and 2 times 1 is 2. It is actually 1, 3, it is 6. Okay. So it is simplest the inner product we know is it's our dot product. It is usually we call it as a Euclidean dot product. Then using this inner product, right? Because these inner products can be different. You can define many ways. If you take one vector like A1, A2, and A3, and you take another vector B1, B2, and B3, you can define your inner product as sometimes you can define your inner product as something like this. You get two vectors and you just define your inner product as something like this: A1 plus A2 plus A3 plus B1 plus B2 plus B3. We don't know, right? You can define something like this. But whatever way you define, I'm not sure that it will satisfy this equation or not. You can define it anyway. But if it to be an inner product, if you define that operation, you can define in any custom way. It should satisfy these three criteria. So if someone if someone give you some operation and tell you to determine whether it can be considered as an inner product or not, what you have to do is you have to check these three criteria and find out whether it is be a inner product. It can be considered as an inner product or not. Fine. Hello. Is it fine or you need another explanation? Because I just go through this inner product because it is not it into much deeper insight that you might have something like, let's say in functional space, let's say you have some, if you say something like fx, right, and you say some function like gx, and you can define some inner product between those two functions as something like this, some integral over some period, right, a to b and fx dx. If these are functions are real, you can define it in that way. Or if these functions are some complex numbers, you can define fx times conjugate g, and you take the real part of this integral. Fine. So it is the way you define it, right? It doesn't matter how you define the function, it is the way you define your operation. But your because this is in fact satisfy your inner product definition, right? This is inner product. This we use most in our signal processing cases, and also using this idea, which I'm teach you next. You can actually think, if you think a little bit, you can see the Fourier series and Laplace transformation and Z transform as the inner product of your functional spaces. If you clearly learn this module, you will see is Fourier series and also the Z transforms and the Laplace transform are nothing but taking inner product with respect to some sort of basis functions. Hello. Fine. Do you need any other explanation? No. Shall I carry on? Because next is up to the Gram-Smith procedure and the distance between two vectors. Hello. Shall I continue? Hello. If I have any problem or I'm too fast, please let me know, right? Okay. Then let's say something like this. Now, okay. I now go to another practical example because this is pretty much important. Let's say you have some point x1, y1. And you have another point x2, y2. And you need to calculate this distance between those two vectors. You know the distance between those two vectors is nothing but x coordinate difference squared plus y coordinate difference square root. The purpose and also some advantage defining inner product is we can also express this as using a dot product. Right? If we take a vector as, let's say I take this position vector, let's say it is R1, and I take this position vector as R2. I consider vector R1 minus R2. And then I can easily see my R1 is nothing but X1, Y1. And my this thing is X2, Y2. And I will get X1 minus X2 and Y1 minus Y2. Okay. So it has my vector difference between these two vectors, position vectors. And if I take the dot product, something like this, V into V, what am I get? I get the dot product into this again, this vector into this vector. So I will get x1 minus x2 squared. Let's say I just write it in this way. We all know that, right? V dot V plus y1 minus y2 square root. So here we define here and we take the square root of that. We clearly see we get the distance between, let's say this point 1 and this point 2, 1 and 2. It means if you have two position vectors, let's say you can define the distance using inner product something like this. If you have two points which has position vectors R1 and R2, you can define the distance as square root inner product something like this. It means you take the inner product of the difference between those position vectors and take the square root of it. Let's say because you take this inner product between the difference vector with itself and take the square root. So the key thing is the distance measure. This is depend on your inner product. Because one can use Euclidean dot product. Another one can use another inner product which satisfies those three criteria. So you need to understand is if you have given two vectors and someone asks the difference between those two vectors, you have to use their defined inner product for that vector space. If they have not defined a vector space for that vector space, inner product for that vector space, you have to use Euclidean dot product, which is the default inner product we use if it is not mentioned. But if it is mentioned, the inner product is defined as this and there's the distance in some sort of a question, you need to use the defined inner product, not the Euclidean dot product. It is pretty important, right? You cannot use this formula for a different inner product. Okay? You got the point? Let's say someone defined inner product some other way. Let's say someone defines the inner product, let's say x1, y1, and you get r1, and you get r2, and it is equivalent to x2, y2. And someone defined this inner product, r1, r2. This inner product is something like 2x1, x2 plus 2y1, y2. If someone defined in that way, you have to use this inner product to calculate this distance, not the Euclidean dot product. Okay? Then actually this will you will have some something like 2x1 minus x2 squared plus 2y1 minus y2 squared square root with respect to that inner product, not the Euclidean dot product. So the distance is depend on the inner product. I repeatedly saying it again and again because in the exam paper, definitely most probably they will give you some problem related to either distance or angle, which I'm going to tell next in the using the inner product. Okay, did you get the point? Hello, fine. Hello, did you get the point? Hello, hello. Okay, so then I'm going to tell you the angle between two vectors. Before going into do that, I need to clarify some equation called, if I don't remember the equation names. It is called not Euclid's equation, actually Cauchy's equation. Cauchy's equation. It means you take any vectors v1 and v2. Okay, vectors. If you get in any product, it is less than v1 norm and v2's norm with respect to that inner product. We define the norm of a vector. The vector is something like this: square root inner product vector with itself. This we are called to norm. Also, this depends on the inner product. That's why I told you in the beginning, when you're doing linear algebra module, you need to forget if you like, let's say the inner product, because in this case, actually, most probably you will like straight away you get the like some feeling that this is the Euclidean dot product. That is not the case, because you have to use the defined dot product for that vector space. So this norm is not the norm we have considered earlier the vector space. It depends on our inner product. So it is something like we define some custom inner products. In linear algebra case, of course, Euclidean dot product is correct. The norm is correct with respect to that Euclidean dot product. But if the linear algebra, if you go into deeper, we have more flexibility to define inner products, and we can define the norm according to that inner product. So that's the only difference. That's why you guys have some confusion all over there. So then you have the angle between those two vectors, something like this. You have the angle, this we call the angle between v1 and v2. We can define it as v1 dot product v2 divided by v1's norm, v2's norm. Okay. So this is actually, if you consider the Euclidean dot product, we have learned from our A levels, we usually write this as v1's norm times v2's norm. You usually put two lines, right? Most of the time, times cos theta. So our cos theta is nothing but v1 dot product, v2 dot product divided by v1's norm, v2's norm. Fine. If you get the point of the angle between two vectors. Hello. Hello. Okay. So then, what do you say about this thing? Let's say I take two vectors, A and the vector B. And I consider the vector A dot B divided by B's norm times you can have also in the vector, this scalar product, you should have considered the scalar multiplication property, right? Scalar multiplication property is like if you take Ka times B, it is equal to K times A's inner product, right? This is some sort of like properties. You have to just go through that, just the property. So then if you consider this vector, right? This vector, what you can say, it is actually, let's say we can write this as B divided by B's norm dot product A's vector, and this is times no, we something like this. Okay, sorry, I think I disconnect from the meeting, right? Okay, I'll explain that again. Okay, so here, let's say you got some vector, right? You got some vector and you got some angle, and I consider this vector A dot B vector divided by B vector's norm times B vector divided by B vector's norm, right? I consider this vector. Actually, this vector is nothing but, these two guys are nothing but unit vector along direction of the vector B. So if I consider this, I can write this as, I consider the Euclidean dot product first, right? Because you get the intuitive idea. I can write this as A's modulus times B's norm divided by B's norm times cos theta times B's vector divided by its norm. So you can cancel this out. You have A's norm times cos theta. You can typically, It is the length of this vector. It means it is the length of, if you draw a perpendicular line like this part is correspond to the length of this part. So which is we call to this part, this whole summation we call, actually we can see, let's say if we take it as, I denote it as A, let's say B or something like this. We call this thing as a projection of A along the direction of B. It means it is look like the projection of, it means if you light a light here, right? If you light a light here, the image of this will be something like this. Again, it means if you, let's say, it means it is a projection. It means like the how much your a vector, the vector's component lies along the direction of your vector B. The interesting thing that you can see is, because there is some cos theta term here, because let's say if you have A and B vectors, you have A comma B vectors, and you have angle theta, you have A's norm times cos theta proportion of that much of magnitude along your direction of B. So what if happen if theta equals 0? If theta equals 0, you have no projection to that. So not theta equals 0, theta equals 90 degrees. You don't have projection to a direction, something like this. If this is 90 degrees, you cannot have projection along this direction or this direction because it is perpendicular. It means if we have perpendicular vectors, it is pretty much easy to handle the vectors more effectively, because if you take any of these two vectors, they don't have any common part between them. Okay, if you got the point. Hello. In the same time, using any custom dot product, we can define our projection to our vector as A dot product B divided by B's norm into B divided by B's norm. This is actually projection of vector A onto direction of B. So using this idea, which we develop the thing called Gram-Schmidt procedure. This process is used to get orthogonal basics. Sometimes we, in process, actually, we can modify this to get orthonormal basis as well. Orthonormal basis is nothing but a basis set. We know these vectors are linearly independent. And also these vectors are orthogonal to each other. It means if you calculate the angle between any pair of two vectors inside this, in the orthogonal basis, the angle between those two vectors are 90 degrees. It means the angle, in other words, they are perpendicular, but not in geometrical sense, in the inner product sense. Okay. Also, we can have orthonormal basis. These are two different words. Orthonormal basis is each basis vector have the magnitude of 1. Okay, you got the point? Hello. Now I tell how you get an orthogonal basis from an existence basis set. That is actually Gram-Schmidt procedure do is you get any basis and convert it and output orthogonal or orthonormal basis. Okay, did you get my point? Hello, did you find with that? Then I'll explain how Gram-Schmidt procedure works. You don't need to remember anything. I'll explain step by step what each step do, and you can do it by yourself. And you don't have to memorize. This is, you get the first vector and this assigned to the first vector, and then we do this. You don't have to memorize any of these. I will explain what will happen. Then you will automatically do what is necessary to do. Fine. Hello? Is it fine? Or you need to any explanation than that? Hello? Okay, I'll explain that. Now, in orthogonal basis, it is something like this. Let's say I get any basis, let's say B1 and B2 into Bn. Now I need to convert this to a orthogonal basis. Or let's say you said get any of the spanning set, not only a basis, right? You can get you get this as a not only a basis, you can even get a spanning set. Okay, you can even get a spanning set to get an orthogonal basis from orthogonal basis from the Gram-Smith procedure. Let's say the first step is you assign the first vector divided by its magnitude to as your first orthonormal basis. At the second step, or afterwards, what you've done is you get U2 as something like this. You get your second basis vector. Then subtract this amount. Let's say B1 into B2 into U1 into U1. And then you're going to divide by the magnitude of this B2 minus B2 U1 minus U1. Okay, look at this moment. What I'm going to do is first I take one vector and assign it to my first orthonormal vector, because if I don't do this division, it is become an orthogonal basis. But if I perform this the division step, if I divide the norm each time, if we, because I use this step to make norm 1, right? There is a way, it is fine if you don't perform this step at each step, right? Then you will get an orthogonal basis, not an orthonormal basis. Okay, so then first we get some vector and divide by norm, it is fine, that is nothing to worry about. Second step, what you do here, I get a vector and subtract some part. This part is nothing but projection of U1 into the direction of B2. It means if you carefully look that about, let's say this is actually direction of, sorry, not B2, projection of B2, other way around, right? B2 in the projection direction of U1. We know U1 is a unit vector. So this thing is represent, you can write this as, because you know it is B2, if it taken as a simple dot product, you can write U1's magnitude times cos theta. You know this is 1. So this is actually the projection amount to the direction of U1. And you multiply with the unit vector, you get how much your vector component has along with the direction of U1. So this is nothing but the projection of the vector B2 to the direction of U1. Let's say U1 is something like this. Your B1, B2 is something like this. This is U1. So you find how much this project into the direction of U1. So then you remove it. Then you only remain the parts which are perpendicular to this direction. Because if you remove the all components in this part, you only remove the components along the perpendicular to this direction. Then you divide it by norm to make the norm 1, then you add up. Third step, or other steps, what you do, you get one vector and remove. Then here, now you have to remove the projection into the U1's direction, because you have two vectors now. U1, remove B3 into the direction of U1, U2, and into the direction of U2, and you need to divide by the whole thing. Whole thing's no. Because in actual sense, you get real numbers, and most probably you will deal with Euclidean dot product in Gram-Smith procedure. You will end up in giving the numbers to this denominator and a numerator, so then you can easily solve that. But the thing is, you get a vector, you reduce the projection of this vector to the previously found orthonormal basis vectors. Sometimes, okay, sometimes this can result 0. it is an identification that this B3 vector is dependent on previously added vectors. Okay, if this becomes 0 means your B3 vector is it is dependent on the previously found basis vectors. Okay, because this is not a basis set, this is a spanning set. If you get a basis set, this situation doesn't occur. But if you get a spanning set, this sometimes this can occur, this can give result as 0. It means there's no component perpendicular to the direction of previously found basis vectors. In this case, actually we only add, we have, let's say we have B3 vector here, let's say we have U1 here and we have U2 here. We only add the components perpendicular to U1 and U2 plane. It means which are not in a direction. It means if you take this as a vector, if this vector is perpendicular to both U1 and U2, because we remove all the parts along the direction is U1 and U2. And if you move it to the fourth one, we get the fourth vector and should remove all the paths along, all the projections along U1, U2, and U3 directions and divide it by now. Got the point? Hello? Shall I need to do with some numerical example and show it how it works? Hello? Hello? Is it fine? Hello? Okay, so I will now going into the vector transformations and tell you some idea about that. If you know the idea of the basis set well, you don't need to have anything to think about the vector transform. It is pretty much easy. You only need to have known the basic theories behind those the transformations. Okay, now I'll explain about the transformations. I just give an insight because I don't want to like fill up much syntax into that. Now you feel like it is pretty much simple. Yes, linear algebra is pretty much simple if you understand the basic concepts correctly. I always, my advice is when you trying to understand mathematics, forget about the syntax, forget about the words or any other like in Sinhala අපි බර වචන සරලවම කියනවා බර වචන අමතක කරලා වෙන දේ හිතන්න. Forget about the syntax, forget about the notations, try to understand what is actually happening there. Then you will understand that there is a pretty much small thing inside, nothing much. But if you trying to memorize all the syntaxes and all the like wordings and the word by word, it will be going to be a history lesson. So don't gonna do that. Okay, transformation is nothing but, let's say I have some machine T, and this machine gets input as a vector and output another vector. We can define this as TV is a W. In simple words, if you give some vector to this transformation, you will result another vector. This type of a thing we call a vector transformations. In this transformation, you have something called linear transformations. In linear transformations, you should satisfy the following conditions. Number one, if you have V1 and V2 vectors, if you get addition and get the transformation, this should be equivalent to the addition of the transformation of those two vectors. It means if you add V1 and V2, consider the transformation of the summation of these vectors. The result should be equivalent to the summation of the individual transformation of V1 and V2. Okay. Then also the other condition is, if you multiply some scalar and V1 with your vector V1 and get the transformation, it should be equivalent to TV1. It means you should be able to get your constants out of your vector. Okay. Or simple words, you can, or else you can take this as a single condition as AV1 plus BV2. This should be equivalent to A V1's transform plus B V2's transforms. Okay. It means if you take any linear transformation of
of your two vectors and you give input to your transformation, your output should be able to the exact same linear transformation, exact linear combination, but not in the vector sense, but in the transformation sense. I will show you some example. Let's say I get some vector, something like this, x1, x2, x3. Okay. I get some transformation, something like this. I get some transformation vector tx, something like this. It is something like x1 plus x2, x1 minus x2, x3 plus x1. Okay. If you consider x, let's say if you put two vectors, like let's say av1 plus av2, this is nothing but the transformation of av1 plus av2 and bv, sorry, it is v11. Let's say how it, let's say it is we put something like vnw to easier of the notation. We can write v1 plus w2, w1. So we can write this as the transformation of the vector av1 plus sorry, this bw1, av2 plus bw2 and av3 plus bw3. You can have any dimension. So what we have to do in terms of x, you have to substitute this part x1, and you have to, in terms of x2, you have to substitute this part, and in terms of x3, you have to substitute this part. And it is easy to verify that it is satisfy all of these equations. If you substitute and see, you will see this will be equivalent to ATV plus BTW. An easier way to recognize linear transformation, if you get this right hand side, these are only linear equations of these coefficients. There are no these powers, there are no e to the power x terms, no anything. These are all linear terms. It means you can only have coefficients and you only have summations, not the multiplications. If in just in case, if you have this type of thing, you can have these are, you can have this, you can tell this as linear transformation. If you, by looking at this, if this has no powers and it has no multiplication, it means something like this. These terms, you can straight away say this is a linear transformation. It should, right? So you can always, you can check for this condition, right? Check for this condition. But as a rule of thumb or just some quick way or shortcut, you can clearly see something like this. Okay. Now, now let's say something like this. You have some transformation, right? You have some transformation. Let's say V. You have it is give some sort of a result. Okay. You know what it says. You have some transformation. Then you know some basis vectors to your vector space which is containing the V. So one other thing is the input vector can have a one basis and output vectors can have different bases. That is totally fine, right? So even you can have something like this. You can have R3 vector and you can output a R2 vector. It means it only has two components. This is also possible because the input side and output side is totally independent. Now, let's say I will draw this diagram. V, and you have input, this transformation, and you have output some vector. Now you have basis for this vector V. Then you can represent this vector V as something like A1, B1 plus A2, B2 and plus something like AN, BN. Now what will happen? I can write TV as transformation of linear combination of these basis vectors AN, BN. And I can write this as A1 TV1 because if this transformation is linear, right? I consider only linear transformation, right? The advantage of linear transformation is I can write this thing as this one. A2 into T, B2 into AN into T, BN. Now what will happen is if my transformations becomes a linear combination of the transformation of the basis vectors. Now, see little bit. I get some matrix, something like this. To this column, I put T B1. To this column, I put T B2. To this column, likewise, to this column, I put T Bn. And I multiply, this is A1, A2 into A. Now what will I get? I will get some vector which is the exact same as this, because this is a linear combination of these vectors TB1, TB2, TB3 and so forth. If I write this equation like this, if I take this as column vectors of a matrix and take this as a matrix product like this, what I get is the same linear combination as this. What is my A1 and A2 and these things? These are coordinates, right? It means if I know the linear transformations of my basis vectors and the coordinate vector with respect to my basis vectors, I can easily get my transformation using this matrix product. This matrix we call the transformation matrix. Got it? Hello? The transformation matrix is nothing but get the basis vector set and you have to place the columns as the transformation of your basis vectors. In this case, let's give a very simple example. Let's say my transformation vector is something like this: x1 plus x2, x1 minus x2, x1 plus x3, something like this. Okay, or something like this. Then, or even I can have one or more page, right? One or more line. X1, let's say plus 2x2 or something like this. And I have to give input of x is equivalent to R3, and I have an output which is in my R4. And I know R3 basis, it is my standard basis, is nothing but 0, 0, 1, 0, 1, 0, 0, 0, 1. And if I get this as E1 and I get this E2 and get this as E3, I can get my transformation of E1 is nothing but x1 plus x2 is 0, x1 minus x2 is this is 0, x1 minus 3 is 1, and x1 minus 2x2 this is again 0. And I can get TE2 nothing but I can get x1 plus 2 1, this is minus 1, correct me if I'm wrong, right? This is 1, and x plus 2x2 this is 2. And TE3 I can get my transformation matrix is something like this. I can get 0, 0, 1, 0. Okay, I can get something like this. Okay, then if I consider, I get some vector something like this. I get vector 3, 2, 4. I get something vector like this. If I get the transformation of this, I can get 3 plus 2, 5, 3 minus 2, 1, 3 plus 4, 7. Then 3 plus 2, 2x2 means 3 plus 4, it is again 7. And also if I get the combination 3 times TE1 plus 2 times TE2 plus 4 times TE3, I get it means 0, 3, right? This should be, I think, x1 plus x2 TE1, right? This one TE3 x1 plus x2. Wait a minute, I think 3 to 4. This 0, this is 0, first element, this third element, and this is 0, and this is one second element only, 1, 0, 1. Okay,
E2 is nothing but X1 X2 it is okay, and then the second one is what is it? Nothing but sorry. I think I need to have the other way around, right? It should be around something like this. It's something like we need to consider the vector space is nothing but okay. So I messed it up. I have to consider this one, right? As 1 0 0. Okay. So E3 is becomes it is 1. This is 1 and 1 0. If I put it is 1 and x1 and 3 it is 1 and it is 1 plus 2x2 it is 1 also, right? Now I have to put E1 is coordinate should be E1 coordinate should be 4, E2 coordinate should be 2, and this coordinate should be 3. Then I can pick, we can see if I multiply by 4, it is 0 plus 2 plus 3, it is 5, equivalent to 5. Then I put it is 0 and minus 2 and plus 3, it is 1. And then I can take 4 times 1, it is 4, 2 is 6, and 4 plus 2 is 6, and 3 is 9. Did I do anything wrong? I think here TE1. Let me the transformation. I think x1 and x3 it is correct. TE2 it is correct, right? X1 and x3 this should be 0. It should be 0, right? Because x1 x3 means these two. It should be 0. So then you can see it is 4 and this is 0 and 3 it is 7, right? It should be give the same answer. And you can see easily 0 it is nothing much and it is 4 and this is 3 it is 7. It means if you write this matrix product, right? If you write this matrix, TE1 is now you have to put actually this 1 0 0 vector, no? So if you write the coordinate vector, you have to write this equation, this 0 0 1 0 1 minus 1 0 2 and 1 1 1 1, and you need to multiply it with the coordinate vector. And B1 should be coordinate vector with respect to E1, B2 coordinate vector should be E2, and B3 should be coordinate vector with respect to E3. Then you get the exact same transformation as this, because it is something like, because this column is with respect to E1, this column correspond to E2, and this column correspond to E3. When you write your coordination vector, you should maintain the same exact order, otherwise you will end up a wrong result. Okay, you have to get the vector transformation of each and every basis and place this as columns. So I put E1, E2, and E3. Then you should have your basis, your coordinate vector also has first component should be component correspond to E1, second component should be component correspond to E2, and third component should be correspond to your third basis vector. And this is how you got your linear matrix vector. In this case, actually you can get the, I think in our exams we will get exact definitely we will get some question. So in this case, actually you can get a question from this part. Any problem up to now? Hello? Any problem up to now? Hello? If you have any problem, you can ask me, right? I just explain what are the real things going on. I repeat, don't worry much about the notations and the wordings. Just understand what happened inside there. You only need to understand two concepts to understand the linear algebra module. Only thing you need to understand up to now, right? There's some other things up to coming up. First thing is the concept of a basis. Second, the concept of a linear combinations, right? And the third, and also before that, you need to understand what is the vector spaces, right? The rules and how they behave. It is nothing but the thing we do with the vector calculus previously. Now we have some them as a rules, which we know, right? We do intuitively or we do automatically, which is now given as rules. So we need to look at them. What are those rules? These are nothing but the thing we know, but give
in some ordered manner, right? You need to get the idea of the basis and a spanning set. Okay, this is the first thing. Then you have to get the idea of the linear combinations. If you know these three, you can easily you can easily see any of the things or any of the what you call things any other than the linear systems of equations, right? Linear system of equations and transformations, also Gram-Smith procedure, and also you have to know about inner products, and you have to develop the flexibility to bear your mind there can be more than one inner product. It means there can be inner products different from Euclidean products. If you can understand clearly these four concepts, you can manage anything up to now in linear algebra. I am guaranteed, right? You can manage anything up to now. And also in other modules, you have some eigenvalues, things, and so on, and you can do anything. Also, you master this well, you can learn machine learning or data science, anything you like machine vision or anything machine learning or anything you guys need to learn. These are the basics of machine learning. If there's no linear algebra, there's no machine learning, right? So you can learn. I will explain it at a later time, but these are the four things you need to understand. Tonight and tomorrow, if you properly go through these four parts and understand what will happen on the and other basic thing you need to understand the linear equation, please look at the Gaussian elimination. Gauss elimination, it is a very simple procedure. And transformation, it is like say in single, it is a GOM part. If you know this linear combination thing, right? And the basis thing, it is a GOM part. And it is nothing much to worry about. The other thing is Gram-Smith procedure. And you need to understand, you need to know some sort of some integration and so on, because sometimes inner products can be given as an integral. Okay. So actually that is the thing I need to teach. And then if you have any problem in your tutorial or a past paper, you can ask me now. And under one condition, it cannot be an assignment problem, right? It cannot be an assignment problem. It can be a take-home assignment, or it cannot be a something you have to submit for a grade, right? If those criteria are satisfied, if that can be some tutorial or problem in example in the lecture or some problem in the reference book, it doesn't matter. I will explain because it is ethical. But if it is something you need to submit to get a grade, it is not ethical, right? So I don't know whether it is like whether it is a assignment problem or not. I cannot know because I don't have very high mental power to do that. But if you are providing that, you take the responsibility. It is not a such kind of a problem, right? Because this is recording. So because I don't encourage those kind of things, right? I always encourage to learn and always encourage to do anything. Also, if you have any problem regarding linear algebra, don't hesitate to call me or WhatsApp me anytime you want it. It is okay before if you call me before midnight, because I usually sleep at midnight. So if you have any problem to ask, please ask. If you have anything unclear or anything to clarify, please ask now. I don't mind even a WhatsApp message now, right? Or in the chat, you can ask anything. Hello. Is there any problem or anything to clarify, or is it all? Or didn't you get anything? That can be also happen, right? If it is, then I can go all over again, right? Because you guys have the exam tomorrow, not me. So I am like to help you. If you don't get anything, please let me know. Those are the four things you need to know. First, before start with vector space, concept of the basis, what is the linear combination, and the linear independency. Linear independency, you have to check. Independency. You can actually, linear independency, you can check it as the linear set of equation. Let's say you have some vectors and you treat them as, let's say you have 1, 2, 4, and 5, 6, 4, these two vectors. And you need to know that these vectors are, these three vectors are, let's say, and you have another vector is 5, 6, 2. And you need to know that these three vectors are linearly independent. What you're going to do? You're going to solve this system of equations. If this system of equation has a solution, means as a solution means these three vectors are linearly dependent. But if this linear system haven't a solution, it means you cannot express this vector in terms of these two vectors. It means these three vectors are linearly independent. Okay. If this system has an equation, this vector has, and this vector are linearly independent. Also, what you can do, another thing is, you can place your vectors as columns in your vector, and you can perform Gauss elimination. Okay. Then if you left with any all zeros row, it means any of your rows become all zeros. It means you have some rows something like this, 0, 0, 0, 0. There's no any non-zero value in that row. It means the set of vectors you are considering is linearly dependent. Let's say you have three vectors, means 3, 6, 7, 9, 8, 1, 1, 1, 1 or something. You perform Gaussian elimination. If you have every row after the Gaussian elimination process completed, every row has a non-zero value, your set of vectors are linearly independent. But if you have any row which has all zeros in it, it means the set of vectors you're considering is linearly dependent. It means you have to deal with the Gaussian elimination. To do that, it is pretty much a smaller thing. If you know the pattern, you can easily do that. Even if it is open book and open internet, you can use use Excel to do that, right? Microsoft Excel to do that. Please clarify it from sir. If you have, it is open book exam and you have allowed to use Excel, you can use Gaussian elimination in Excel as well using the cell operations. You can use some tutorial as well, because in Excel it is pretty much easy to do Gaussian elimination. You have to choose what are the operations you're going to do, but it is pretty much easy. You don't have to do it by hand. You can perform the row operations at once for each row using the cell operations given by Excel using the formulas. Okay. Is there anything to clarify? Hello? Anything? I know it is too late to conduct a Kuppi, right? It is tomorrow is the mid exam. So if you guys want to do prepare more for the second meet, please let me know in advance so I can conduct probably more than one Kuppi, right? Probably 1 or 2 or 3. I don't mind, because I know we will need more time, right? I know I go too fast, because if I explain everything and do every bit of thing, we need to expend about 4 to 5 hours. So it is not going to be the case when you are conducting online Kuppis. So you have to conduct in within 2 hours, otherwise you will feel pain and eye strain and so on. So even I can't concentrate on the online session more than 1 hour, most probably 1.5 hours. So please let me know in advance, so I will more than happy to help. So if there's no problem, I'll end the session and I'll share you the recording. Also, there's a recording on my YouTube channel as well, which I did for your senior batch. You can also refer that as well. And I will also share that recording. I know I go pretty fast today because I have to cover a lot of content, right? But my overall motive and the thing I want to give you is the linear algebra is nothing much. There's very small things you need to understand. If you understand these basics, there's nothing much you have to worry about. You can easily go through the exam. So, okay. So if there's no questions, I end the recording. If there's any question, you can ask now. I will like stay here about 5 minutes. Okay. So silence means there's no problem. So I'll stop the recording